Okay, let's continue from the point where we talked about the time of the steady state, time to reach a steady state. We see we the point that I just finished. We said that this is independent on, this is an important thing, independent on the used R or K node. It's only depends on one thing that we will talk about it in a minute, which is only the half-life, or K, which is the rate of elimination of a constant of the drug. So we mentioned that to reach the steady state, the true steady state, we can, by changing this, in addition to it depends on K and VD, so RK and VD, and the growth it's mainly dependent on R. We said that this is called the true steady state. But as we know already, something that we can't reach, we need to go around it and to have what we call it practical steady state concentration, the thing that we need to or be able to measure, which is usually, you will have in your slide number 23, you will have the definition of it. If we consider this our true steady state concentration, it's either that we are within 5% of the true steady state, or we reach 95% of the steady state concentration. So as definition, I will read it. It's when the plasma concentration of the drug is within 5% of the true steady state concentration, or in other words, when the plasma concentration of a drug and the blood represent 95% of the steady state, true steady state concentration. Okay, so it's similar to whatever we know about the elimination. This happens, so you need 5% or more for sure, which means of the, to reach the steady state, which means this is the 5%, which means that you are reaching 95% or more of the true steady state. This happens either, and you have the table on your slide 23. This happens, the 95% of the steady state happens at 4.32 half-lives. This is the number of half-lives, or N. And if we want, this is for 95% of the steady state concentration, or more than that, such as 99% of the steady state concentration, and this happens at 665 half-life. And those numbers you need to memorize because they are important. This is similar to whatever that we know about the 5 half-lives, but the exact number, even there, it's 4.32. So the half-life, if you have 4.32 half-life, you will reach 95% of the steady state. If you have 6.65 half-lives, you reach 99. So we will consider, again, if I ask you a question, I will tell you, for example, let's consider 99% of the steady state is enough. But usually we consider that 4.32 half-lives are enough to reach the practical steady state. So from now on, you will, in any calculation that you will have, you ask yourself a question. This is an infusion, an IV infusion. The time that you have, is it more or equal 4.32 half-lives or not? If it's more or equal, then you are at a steady state. If yes, you are at steady state. If not, you are not at a steady state. What does this mean? This is 6. It means that we have this concentration equal R over K multiplied with VD, right? This is the general equation. Whatsoever the time that we have at steady state, we set this equal R over K multiplied to VD. So we have it either at not steady state or before steady state and at steady state. So you will ask yourself the question, if the time that we mention, is it half-life? If yes, then we will use steady state equation, which is equation number 2. And if not, we will use equation number 1, not steady state equation. Okay, or the general equation. Okay. بالعربي إذا أنا معطيك وقت معين بغض النظر شو هذا الوقت بتروح بتقسمه على شو؟ على half life. Okay, this is the time over half life. If it's تسأل حالك if it's equal 4.32 or more, then you are here. وبنشوف هذا الحكي وإحنا بنحل. Okay. هلا بالنسبة ال 95 or 99, which is the table that you have beside 23, 99, 95, 96, whatever the question that I'm asking, can we determine من وين, from where we get this number, or 6.65 or any other number? This is what is explained on your slide 24. Okay, we have this equation for a steady state and we have this equation for the general kind of thing. Can I determine when is the time to reach 95% of the steady state? This is the question. For sure, you can ask the same question for any percentage that you want. So I need to use this general equation, okay, and to determine when I will reach 95%. To reach 95% of the steady state, it means this is the concentration that I need, which is steady state concentration, and I will have 95% of it, right? Which will be equal to R K V D 1 minus K time over 95. Okay, this is what, substitute this R K V D. I need 95% of it equals R K V D 1 minus 95%. Okay, what will happen here? This will goes with this because we are talking about the same drug and we are having the same conditions. So play around with the equation to have the time to reach 95% of the steady state. You will have 9 time to reach 95% of steady state concentration, which will be equal 4.32 half-lives. Okay, for sure you will have this in terms of half-life. Okay, the same thing that you can have it whatever the percentage here. Try it with 0.99, which is 99. You should have 6.65. Okay, now again from now on we will consider in our calculation the practical steady state is the steady state that we are okay to have, and we will use this equation for it. I know it's there to just as a true steady state or as a theoretical steady state, but for calculation we will consider that 5 half-lives are enough to reach the steady state. So we will consider 4.32 as enough to use the steady state concentration equation. Okay, another point to take into consideration is if we are having this profile. So let's consider this what you get, concentration versus time for IV infusion whatsoever. This is a continuous infusion, okay? Which means if you didn't stop the infusion, it will continue whatsoever. The steady state will continue, right? Until you reach infinity, which is, again, we don't do it in practice. We can't reach it. But if you don't stop the infusion, it will continue forever, right? What if I stop? This is your time to reach a steady state. Okay, so this is your steady state concentration. What if I stop the infusion either here or here? Which means Either I stop the infusion before steady state or after a steady state. Do I have a difference in whatever that will happen? Again, if we remind ourselves of whatever that we have in this model, we have R, which is the infusion rate, and we have K, which is the elimination rate. So we have this, and we have this infusion rate. This is zero order, and this is first order. This is what we have, right? This is my equation here, my model for this, which I will have the equation that I just mentioned, but I don't care about the equation right now. Again, we are talking about one compartment, and we are talking about single dose. So the same model that we talked about. Let's say in both here or there, I'm just terminating this. So I will continue whatsoever. In this case, I will use it the fuchsia, okay, compared to this, which will be the same, but will continue until here. So the infusion will continue until I reach the point of termination. Okay, so this is termination point, and this is termination point. But either I'm stopping it at steady state, or before steady state, or after steady state. So I'm stopping this. So by default, the question is, if I'm on rectilinear graph, what will happen for the profile? So let's start with this, okay? This one. If I stop here, so we don't have this, what will happen, right? You stopped this, you'll have only elimination, and the elimination is first order. On rectilinear, it will act as first order, okay? The second part, we have this, again, I'm stopping it after reaching the steady state. We'll have it the same, and it will be similar profile to this because it's a first order, so K is the same. So it doesn't matter I'm stopping it at this point or after that, the profile will decline. And sorry, I keep missing the mic, but anyway, the profile will decline in similar way because we will have only elimination, whatever, if I stop it here or if I stop it there, okay? If we have the same thing but on similar profile, according to whatever you know about the elimination only profile, and semilog, the first order and rectilinear, let's remind ourselves, CB versus time, on rectilinear, it was like this, elimination only, right? On semilog, CB versus time, it was like this, which means in the first profile, this is our supposed to be our profile. And the first profile, if I stopped here, I will continue until I stop, terminate. Okay, so this is our case. The second profile, I will continue until I stop, okay, but it will decline. And let me just correct this, and same slope. So this will be parallel to this because the elimination is first order, which means the slope will be equal minus k over 2.303, which can be determined by linear regression if you have log or len, right? Or if you have 2 points, you will have it minus k over 2.303, and you can by this determine the half-life of elimination, right? So the idea is whatever that you terminate before the steady state or after the steady state, the profile will decline as mono-exponential if you are on rectilinear, or it will show you a linear a profile if you are on semilog or log CB or len CB, and we can use it. So if we terminate the infusion, is one way to determine K an IV infusion, so termination of the IV infusion to determine the slope of the decline, which will be your K or a rate constant, elimination rate constant. Okay, so let's go with the first practice exercise, which is very easy, but let's go with it. So if you have, this is the exercise that you have on slide number 27. Okay, so if you have volume distribution equals 20 liter and K 0.231 or minus 1, this drug is given as IV infusion injection with a constant infusion, which is R, equals to 250 milligram per hour. It's asking you to determine the concentration at 2 hours of the drug infusion. Okay, so remember, you need to ask yourself a question if you are at a steady state, yes or no. Okay, and to ask this question, we said that you need to determine your half-life. Okay, when you go here and determine your half-life, it's equal 0.693 over K, right? This will be equal to 3 hours. So your half-life is higher than 2 hours, which means that I'm not in steady state. Or other words, does 2 hours over half-life, which is a 3, more or equal 4.32? No. So we are not at steady state. So this is our case. We are not at steady state, which means that it's equal R K VD 1 minus K time. To substitute, this is what you need are 250 milligram per hour. So this will be, let's write the unit. Okay, this 0.231 hour minus 1. This is 20 liter, 0.231 hour minus 1. And this is the time that you want, 2 hours. Then the concentration that you'll have is equal to 20.02. The unit will be milligram per liter. And this is your question, the first one. The second one, which is the same thing, even it's giving you, I will write it again just to, okay, you will have volume distribution that is equal to 20 liter, and you'll have K that is equal 0.231 or minus 1. You have concentration at 2 hours. I'm giving you the same number just to give you an idea what I'm asking about, which is similar, but I'm asking about something else. I'm asking about R. Okay, so it's similar to this, but I'm giving you that this equal 20, or which is the same number that we have here, and I'm asking you to determine what is R. The same thing, substitution to and of the number, and you will have R equal 250 milligram per hour. Just try it by yourself and you see it's the same. I will just go with the third question. And then we will stop it there for this video, inshallah. So exercise number 3, which is your slide number 29. Okay, you have a patient with was given an antibiotic with half-life that is equal to 6 hours, and you have a constant IV infusion rate with 2 milligram per hour. At the end of 2 days, this is the time that you have, which means this is 48 hours. We have a serum concentration that is equal to 10 milligram per liter. This is at 48 hours. Okay, calculate the total clearance of this antibiotic. So it's asking you about the total clearance of this antibiotic. Okay, again, you need to ask yourself, am I at steady state or not? to determine this, you have 48 hours and you have 6 hours as half-life. So whatever that you need to do is to determine either you are at steady state or not by knowing if you have 4.32 half-lives. How you will do that? You will do what? Time, right? 48 hours over time of that I'm asking about, which is infusion time, which we stayed until 2 days, over half-life, which is 6, right? It's 6 hours. So this means that we have 8 half-life. Is it more or equal 4.32? Yes. So it means that we are at steady state. Okay? So if we are at steady state, we will say that concentration at steady state equals R over K multiplied with VD, or R over total clearance. We have this as 10 milligram per liter. We have this is 2 milligram per hour, and we need this, right? Then you will have the total clearance that is equal to 0.2 liter per hour, or 200 milliliter per hour. And we will stop at this point.